Hi there, I'm Graham Lewis, and in this short video we're going to discuss scientific notation, writing numbers that are really big in a more convenient way, and writing numbers that are really extremely small, very close to zero, in a easier way. So let's start with the speed of light. The speed of light's always fascinated me. It's an interesting thing to consider. It travels at approximately 300 million meters per second. So if I want to write this in scientific notation, what I need to always remember is that there has to be always one number left of the decimal point, and that number can't be 0. So only one digit here, and remember it can't be 0, so don't include 0, so one digit there. Then I've got 3. I could write 3.0, I can write 3, either's fine. I think I'll take away the 0.0 now, because now you've got the idea. So 3 times 10, how many times do I have to times 3 by 10 to equal 3 million? Well, I always like to hop Mr. Decimal Point. So here we go, 1, 2, 3, 4, 5, 6, 7, 8 times. So if I multiply 3 by 10 8 times, I will get 300 million meters per second. So we know therefore that in scientific notation 300 million is 3 times 10 to the power of 8. And we could put 3.0 times 10 to the 8 if you want, both would be correct. But we don't need any more zeros there. Remember that there's only allowed one digit left of the decimal point, and something else to notice, it always has to be a multiply. You can't have a divide there, it always has to be multiply. That comes in this second example here. Considering we're thinking of a small number, and I've got here 0.00000015. That's quite small, quite in size, quite small to 0, quite close to 0. This is actually the size, approximate size of a malaria pathogen. So if we want to have to write this in scientific notation, really what we're doing is we're taking the decimal point, only one digit left of the decimal point again. Remember, only one digit, and it can't be 0. So one digit, not 0 left at that point. I need the 0.5 now. I don't need any more zeros there. You can ignore them because 1.50 is the same as 1.5. Now clearly I'm dividing this by 10 lots of times. And if you watch my previous video, you'll know that when you divide by 10, it's the same as timesing by 10 to a negative power. So let's hop Mr. Decimal Point. 1, 2, 3, 4, 5, 6. There he goes. So to the power minus 6. So if you want a little refresher on why 10 to the minus 6 is the same as 1 over 10 to the 6, so it's the same as dividing by 10 6 times, you can watch my previous video on negative powers. So that's how you deal with really small numbers close to 0 in scientific notation. Remember, for really large numbers that the power will be a positive number, and for really small numbers close to 0 it will be a negative number. Remember, there's always got to be one digit, not 0, left of the decimal point. Let's do another example. So let's go the other way. Imagine I had 569, and then I'll just pile on a lot of zeros there. And let's write this in scientific notation. So it would be equal to 5.69. How many places is Mr. Decimal Point moving? Let's count that. There we go, so just hop him along. And how many did you get? You should have got 10 at 11, so times by 10 to the power 11. Now let's try one more. Let's do 0.000030012. Now this is a small number, so hopefully you're thinking it's going to be times 10 to the negative power. So it's got to be 3. I need the 0.012 times by 10. Let's count. 1, 2, 3, 4, 5, 6. Whoops, sorry, I went too far there, didn't I? Let's go again. 1, 2, 3, 4, 5. So there it is. So minus 5, because it's a number very close to 0. It's a very small number in size. And that's how to write numbers in scientific notation. Now obviously these aren't that big and that small numbers. You can get really, really big numbers. So imagine we had 2.3 times 10 to the 46 and 8.3 times 10 to the 12. If we're looking at those numbers, which one's bigger? Well, really clearly you're timesing by 10 46 times here, which is way bigger than timesing by 10 12 times. So even though 8.3 is bigger than 2.3, 2.3 times 10 to the 46 is way bigger than 8.3 times 10 to the 12. And I'm sure you can imagine in your head, writing this number out with all the zeros would be absolutely horrible, which is why scientific notation is really useful. So clearly 2.3 times 10 to the 46 is way bigger than 8.3 times 10 to the 12. And equally, you can tell on size of really small numbers as well. If I had 6.2 times 10 to the minus 17, and I had 5.3 times 10 to the minus 49, which number's closer to 0? Which one's really small, close to 0? Well, it's the minus 49, isn't it? Because you're dividing by 10 49 times. You've got loads of zeros before you get to the 5.3. So clearly 6.2 times 10 to the minus 17 is going to be a bigger number than 5.3 times 10 to the 49. Because imagine all the places you need to move the decimal point here. 49 places. 49 places. Whereas on the 6.2 one, you're only, still a small number, you're only moving it 17 places. So 5.3 times 10 to the minus 49, much smaller. Well, I hope you've enjoyed that video on scientific notation. If you're interested in doing any more number problems, maybe you'd like to look at one of my BEDMAS problems in order of operations. Thank you.